Can you s- uh, show the video, sir, Chandan sir and Saibal sir? And it will be good. 1 minute. I want to accept few peoples too. Yeah, we have enough participants now. So the yeah, I want to give a brief bio of our speakers. Mr. Sebal Ghosh, he's a manager of Eastern Regional Load Dispatch Center, ERLDC. It's previously called as POSOCO. Now it is Grid Controller of India. So, he's holding the MTech degree in Electric Power System from IIT Dhanbad, and he's a senior member of IEEE and PIS and SIGRI. And he's the member of various schemes in POSOCO. So he got proficiency in high level proficiency in PSCAR and PSSC, and a protection reliability coordinator for international corridor for Indo-Bhutan and Indo-Bangladesh. And he's got some experience and in dynamic model building Bell working group of that, and built practical model for Bell excitation systems, and also built a complete dynamic model for Eastern region of India, and the dynamic study of islanding logic design for four island schemes in Eastern region too. So that's the brief profile for Saibal Ghosh. And our second speaker, Chantan sir, is actually Chantan Kumar. Actually, he is a chief manager operational planning for ERLDC Grid India, and also he is also a senior member of IEEE and IAT. And he has got a he's a vibe. I know he a lot of lot previous years itself. So I so much admire to his work and technical also, and also in publications wise also. So a very warm welcome to you people, sir. So thanks to join with us for a live session and all. I think we are eager to listen to you for getting better knowledge in power system oscillation studies and all. Yeah, stage is yours, sir. You can hold it there. Yeah.
Yeah, thank you, Satish ji. Yeah, good evening, everyone. Good morning to many of you, those who are connected from the US side and the Canadian side. Thanks, the Kerala chapter, PS Kerala chapter, for inviting us for delivering this session. And certainly we will try our best to share you the practical wisdom, because too much theory is always not good. So we will be sharing you a lot of the practical experience that we have gained in the area of the small signal stability, and how we can improve the system. But prior to that, just about the Grid Controller of India Limited. That's the company in which we are working. It's a 100% company that is being owned by the central government of India. And this means basically now it is under the Ministry of Power, basically. And the job of this is basically the Grid Controller of India Limited, earlier known as the Power System Operation Corporation Limited, POSOCO. So now the Grid Control of India Limited is the, means the national, you can say the system operator, the ISO of the Indian grid, basically. And it coordinates with the international counterparts like Nepal, Bhutan, then Myanmar, and this Bangladesh, basically the four countries which are interconnected also with the Indian power system. So that's the job that we have. And we have basically one corporate center at Delhi. And apart from that, we have one national control center at Delhi, and then the 5 regional control center. One in Kolkata, the eastern part, western part is in Mumbai, Western Load Dispatch Center that we call. Then we have Southern Load Dispatch Center at SRLDC at Bangalore. Then we have Northeastern at Shillong. And the northern part, the Northern Load Dispatch Center is at the Delhi itself. So that's the brief about the Grid Controller of India Limited, which is the ISO of the Indian power system. So I am handing over the forum to basically to Sabal, who will be taking us through the tool of this low frequency oscillation case studies also. So Sabal, please, yeah.
Thank you for the introduction, and thanks to IEEE Kerala chapter for giving us the opportunity. Just let me share my screen first. Is my screen visible?
Yes, yes, yes.
Yes,
Perfectly
Subha.
visible. Yeah, yeah.
Yes, you can go on the full screen mode. Yeah, yeah, it's now full screen. Yeah. Thank you.
Yeah. So this will be basically the small signal stability power system. So that is manifested in the system in the form of low frequency oscillations. And these oscillation can be triggered as from the name also, like without even any large disturbance, there can be some kind of oscillations in the systems. So for that, first we will just understand with few very basic theoretical parts. And when we are discussing all these kind of oscillation, this is basically so far Indian grid is predominated by the synchronous generators. And recently what happening, some energy transition is happening. And that's why lot of IBR resources are also getting connected. So there also we are seeing some kind of oscillations. But what we will be focusing today, basically on the oscillation that we used to we are used to in our classical studies, like very large masses of synchronous generators oscillating against each other. So in these oscillations, there are two governing force or torque. One is synchronizing torque, and another is just uh, another is this damping torque. So from the name also we can understand that the synchronizing torque tries to maintain the synchronism between two components. What are those two components? We'll see in the subsequent slides. And the damping torque is basically a torque that tries to damp out any oscillations. So from our classical theoretical part, we know that this equation that is shown in the this top right corner, this is the basically the torque equation of a synchronous machine. If we are talking about a single machine, infinite bus kind of thing, so this is the arrangement. So now we are talking, this equation is without any PSS. So here we can see one component is double derivative of delta. That means this is the acceleration component. One is your derivative of delta. That means this is the speed component. And another is delta directly. These three components. These are the basic governing equation of a oscillation, like a synchronous machine. So like the last component, this is basically the synchronizing torque. Why it is synchronizing torque? Because we know when a spring we stretches it, there are some force developed, and which is simply proportional to the stretch of the spring. So its function is just to reduce that stretch. It acts against the stretch of the spring, and in case of generator we can say that it acts against the loss of synchronism. So that's why this component is the synchronous component. And this is our like damping and synchronizing plane. So this axis, this vertical axis is nothing but this is the synchronizing axis. So synchronizing axis means the delta, any change of the rotor angle, that will be basically aligned with this axis. And whenever we are talking about a small signal stability, we know that we this equation of the power system, synchronous machines, these are some non-linear equations. So we have to linearize it around the point of operations. So when we linearize, that is basically we take a very small change around the operating point. So this delta component is acting along the synchronizing axis, and the speed component. Speed is nothing but the derivative of change in delta, right? So and we know that derivative leads its original component by 90 degree. That's why it is in the leading direction by 90 degree. So this is the overall damping plane of a synchronous machine around its operating point. Now, when and this x-axis, this is the damping axis. So this vector right now, it is the resultant response of the overall operating of a synchronous machine. So that from this we can see that it is providing some synchronous torque in the positive side as well as some damping torque in the positive side. That means this is kind of a stable response, and you can see from the response as well. Now, which thing introduce some negative component in this, either negative damping or negative synchronizing torque? That we'll see now. So the first picture, this is a very basic picture. It is without any PSS. Now the right one is with this one is with PSS. Now, before understanding the effect of PSS, let us understand the effect of AVR itself. So AVR, is my full screen is visible, these equations? This equation
Yes.
is visible.
Yes, sir.
Okay. So this equation here, we can see that another extra term is being added to the torque equation, that is K2 into delta EQ. So this is basically the term of excitation. The previously what equation is shown consists of only the first three terms. That means these are the natural expression of a synchronous machine without any excitation control. Now, when we are adding some excitation control, it is adding some extra term. Now, this extra term, you can see this dotted line, or here in the below side. I hope my pointer is also moving and it is visible. So this is that this regulator action, and what it can do, it can bring this resultant which was previously in the positive damping side and positive synchronizing side. Now it is coming into the negative damping side due to this very high high response excitation system. So that's why you can see that this resulting torque is becoming unstable, right? So as we know that from fast swing stability, very high response is good, but sometimes this can introduce another kind of small signal stability issues. So to take care of this, we need to again modify this K2 delta EQ part using some other supplementary control, that is the PSS control. And it basically acts how PSS acts. PSS based whatever there is deviation from the speed, or you can say the delta. So PSS acts, introduce some voltage, excitation voltage in that direction, in the opposite direction. So again, the overall resultant of this all the operating forces turns into the positive damping quadrant and positive synchronizing quadrant, and that's why the resultant response again stabilizes. Now I have talked a lot of theoretical parts here, so those already who are doing their in their studies, they may get it very quickly. Now we'll be seeing these all the terms that has been explained in terms of some practical explanations or practical examples. So whatever is being explained in the previous slide, that is been written here only in terms of like this damping part and the synchronizing part. Other two parts has been removed. So this is the basic two component which decides the stability of a machines. And all these are like very big equations, so we are not going to discuss, or there is very difficult to understand all these big equations. So now these are look at this picture. This is a real system response. So whenever there is some transient, there some oscillations comes, and depending on the damping torque, what is the present damping torque available in the system, these oscillations die down after the transient. So what it does, any transient in system basically ignites all the natural mode of oscillation in the system. Now, if system has enough damping torque, then this response will die down. And if system don't have enough damping torque, then this oscillation will like grow. And this oscillation not only needs to be triggered by some big transient, even sometimes very small change in a like you just switch a reactor to control the voltage, that can also trigger this kind of small signal stability issues. And another, in the last part, you can see there is some called forced oscillation. Forced oscillation, what does it mean? Say, for controlling, there are a lot of equipment, lot of generators are connected in the system. So to control them, we have controller for every individual equipment. Now, if any controller malfunction and it by default generates some cyclic command, say in a governor, or we know that it's generated steady power output command from the generator. Now, say suppose due to some maloperation, there are the output of the governor itself become oscillatory. So that introduces a forced oscillation phenomena in the system. So here, this is the first one is the natural response, and the second one is the forced response. That means in the first here in this transient, we can see that we are perturbing the system either with a step change, we are giving a step input, or an impulse input into the system. And in the forced part, what we are giving an oscillation of certain frequency as an input to the system. And now system is responding to that. So these are the like pictorial demonstration of different kind of torque available in the system, all these things, and how during the oscillation, how this angle varies over this power angle, this P delta curve that is basically shown here. Like this way, the angle keep on varying during the oscillation. So these are some graphical representation, and again these are damping and synchronizing plane has been already explained, so I am skipping this as of now. And if I am going too fast, you can ask at any point. So again, these are some very basic explanation of the oscillation phenomena. Like we know in steady state, the electrical and mechanical power is balanced, electrical and mechanical torque is balanced. Whenever there is certain kind of disturbance, these two does not match with each other for certain amount of time till the oscillation is damped. So that time either at certain point of time, electrical torque is more than mechanical torque. At certain point of time, mechanical torque is more than electrical torque, like that. So this basically constitute the oscillations, and to damp the oscillation, we need to bring this torque again together, and for that we have these PSS. Now, these are the basic phenomena, how oscillation is created and what oscillation control mechanism is there that we have discussed. Now we will be discussing what are the different mode of oscillation that is being observed in the real system. So we can, like for analogy, we can think about that lot of masses like these are connected with each other through some rubber bands, and these masses are of different weights or different strength of this rubber band are different. That means the interconnection or the equivalent impedance seen by one generator that are different. This signifies that only the strength of this rubber band means nothing but the what is the equivalent impedance that is seen by a generator. Now here, if we just give a sudden shock to any one of the weight, the whole system will initially have a transient and will move. Now in this movement, what can happen? 2-3 masses can form one group and they move in a synchronism, but it is against another group of masses. That means this A, B, C, they can be form one group and they move synchronously, but their movement is different from another group, that is D, E, F. So this is an example of inter-area oscillations. Now, from that damping and synchronizing plane, we can have an explanation of different kind of oscillation that can happen in the system. First one is the normal, and which is well damped. That will for few milliseconds, the oscillation will be there for 2-3 cycle, and it will be damped out. That means here the synchronizing as well as the damping torque is positive. But if the damping torque is 0, that means if one oscillations come, that oscillation will sustain, like its magnitude will remain same. And if damping factor becomes negative, what will happen? The oscillation will be magnified over the time. Now, oscillations frequency, how that is determined? This is basically linked to the mass of the synchronous generator which are oscillating against each other. So now if we talk about only single generator oscillations, then its single mass or its own mass will determine the frequency. But when we are talking about the inter-area oscillation, then how the group is formed, like whether in the group there are 2 generator or there are 30 generator or there are 50 generators, like that, the overall inertia of that group will determine the oscillation frequency. And as we can see that this H term, this is inertia. That means this is related to the mass. So when the large number of generators forms a group and oscillates against each other, that is inter-area oscillation, that time in the denominator very high value is coming because it is the combined mass, and that's why the oscillation frequency is low. And like the oscillation factor depends on these three, oscillation frequency depends on these 3 factors, because as we have already mentioned that it is a nonlinear equation at which point the system is operating, that is very important. So this is denoted by this generator output level, and system strength is nothing but the equivalent impedance seen by a generator. That means, how say only think about one generator is oscillating against the system, right? So whether that generator is connected to the grid through only one single line, and that is very long line, that means its impedance value will be very high. So the effective system strength that is being seen by the controller of that generator will be very low, and that's why there are chance of oscillations when there are weak interconnection, and inertia is already explained. So these are the different frequency range. I think this is more or less known to everyone that inter-plant frequency, like this local mode of oscillation, when one single generator oscillates against the grid or the group of generator within a single generating station oscillates against the grid, that frequency lies in the range of 0.1 to 2 hertz. So this will be little higher frequency as mass is less. And when interplant oscillation is there, that means one unit of a plant is oscillating against another unit of a plant. In this case, the oscillation frequency is even higher, and it is in the range of 1.5 hertz to 3 hertz, because here both the oscillating units have very small mass. But in the first case, what happens? In one side there is an infinite grid, and in other side a single machine. That's why this frequency is little less. But in the intra-plant mode, this oscillation is not at all seen outside the plant. It is completely inside the plant. If you look at the power that is being exported from the overall plant, there will be no oscillation. Here, oscillation is purely between two units inside the plant. So this oscillation frequency is more, and inter area, it is very low frequency, that is in the range of 0.2 to 0.4 hertz. And there are some like small area can be formed, that is we are calling intra area. That means they are not far away, they are very close by generators can form to group and may oscillate against each other. That is coming under this category. So these are the different pictorial representation of different kind of oscillations. So here you can see that when only one unit is oscillating against the whole system, that is intra-plant. And when two units of the same plant or very nearby plants oscillates against each other, that is interplant. And this oscillation will not be observed outside in any system, it will not be observed. Likewise, for this also, this intra-plant also, this oscillation will only seen in the output of these lines. And maybe after one or two level, it will be visible, but as we move away from the plant, there will be no oscillation. Whereas inter area oscillation, these can be visible thousands mile away also. Like oscillation will persist all over the Indian system, and it can be visible by every plant in the system. So again, these are the what are the different type of oscillation that has been again explained here, which I have already covered. So I'm just skipping these slides. Now, these so far we have talked different kind of oscillation. Now the question next come, how we can detect a oscillation. Now again, when we are talking about detection, there comes two option. How we can detect even before the operational horizon. Like in real time oscillation is happening, that time we can detect from the measurement of power flow, voltage, reactive power flow, lot of things are there. But how we can prevent even before this oscillation is actually taking place in the system? So for that, in the offline, we need to do eigenvalue analysis, lot of dynamic studies in the simulation software, and based on that we can identify whether there is any low frequency oscillation probability are there or not. And in real time, from the measurement using the PMUs, because these oscillations are generally very fast as compared to the sampling rate of a SCADA, because SCADA every 10 seconds it's updates. So that's why these kind of oscillation of 1 hertz or 2 hertz, that means their time period is 1 second. So with a sampling rate of 10 seconds, in SCADA, you will not be able to capture all these oscillation. But using PMU, you will be able to see these oscillations. And in PMU, there are like some already designed methods are there in the PMU engine to detect oscillations. And in the outside also, using your own algorithm, you can develop some detection techniques. So what are the different technique that has been mentioned here? You can do FFT. So if everything is in steady state, then what will be the output of your FFT? It will be a DC component, right? But if there is some oscillation, low frequency oscillation, so you will get spike at that frequency. So using that, you can detect which kind of oscillation it is. Whether it is inter area or intra area, like that. And these methods are almost similar method, but has some additional complexity in their calculation algorithm, and that complexity gives you little more information about the oscillation. Like what is the damping? In FFT, you will just simply get the frequency spectrum. But what is the damping? All these things, it will not be given by the FFT. So for that, you have pencil matrix pony, all these things. Now this model-based analysis, that means simulation. Whatever we have modeled in our simulation software, based on that, we can do some analysis and we can identify the oscillations even before the operational horizon. So these are basically based on some mathematical model, provides you information regarding the natural mode and where they are observable, where they are controllable. All these information you can get from that eigenvalue analysis or model-based analysis, simulation-based analysis, and help you to identify the cause and effect, all these things. But what are the disadvantages? Because if you model something in a different way than their actual behavior, then you will get a completely wrong result. So you have to be 100% sure that your model is exactly representing the behavior of the component which you are trying to model. Again, it to analyze this kind of oscillation phenomena, you have to do lot of oscillation studies and lot of simulations, and it is quite difficult. And this also takes some time. So you during real time, when you have to take decision within some 30-40 seconds, or even sometimes before that, it is difficult. And that's why in DSA tool, this utilization of this kind of methods is little difficult. And also its output depend on the initial conditions. That means in a day, if we talk about different operating point, in the night hours, demand is high, all generation are doing very high output. So that time, one kind of result you will get. In the off-peak hours, like in the morning 5-6 hours, when all lights are off, demand is very less. That time, all the generators are running at very low load level. So you will get some different results. So in a day, you have to do lot of study like that. Now, against that, what the measurement-based analysis, what are their advantages? They are no complex mathematical model is required. Based on the analysis of the signal using some curve fitting or other algorithm, as already mentioned. It's very faster and real-time observability. It gives you like where the oscillation is being observed in the real time. So it gives you the exact location. In simulation, what you can say that this may cause the oscillation, this may cause some problem like that. But when you are doing it based on some measurement in real time, that time you know exactly what is doing this oscillation and where this oscillation being generated. So you can like identify the root cause little faster. Now here, as we mentioned, like if you detect the problem in real time, then you don't know what action you need to like not don't know. It is like you don't have any controllability over that beforehand. So after you like notice the oscillation, then only you can take some as like action. But in the model-based analysis, if you see that there are some scope of further PSS tuning with which you can damp the oscillation, then you can do it before that oscillation has come. But in the measurement base, once the oscillation has come, after that you will be able to take some like response. And when there are a lot of mode frequency are there, which are very close to each other, it is difficult to segregate between them. And how to improve the damping of any mode, that is also difficult in this decide in this measurement based analysis. So these are the different information, useful information for the oscillation. What is the mode amplitude? That means what is the peak amplitude of these kind of oscillations? That is the mode amplitude. What is the mode damping? That we know that from the first peak to second peak, how fast it is damping down. From that, we can calculate the damping ratio. So this gives you the mode damping. And this is the mode energy, like how the energy of this mode is flowing into the system that you can take. And you know that there are one method which is called like energy flow based oscillation source detection method is also there. So using that, you can detect this mode energy direction based algorithm you can develop to detect the source of oscillation. And these are the mode shape. That means in your system, there are thousands of machine or thousands of like buses are there. So during the oscillation, whether which buses are oscillating against each other, that information you can generate using their phase angle of this oscillation. That means, what does it mean by phase angle? At every bus, the voltage or power is oscillating with some frequency. And if you plot all of them, then you will see that some when in one bus, one particular bus, voltage is increasing. At that same time, in other bus, voltage is decreasing. Like that, that means they are in the opposite direction. So based on this mode shape, you can decide which are your coherent groups in the system and which are participating in the oscillation. So here we can see that these I think this is Solapur and this Vindhyachal. These are in one direction and rest are in the other direction. So these this is forming two different groups, and there may happen some generators are in the perpendicular. That means they are not participating in this oscillation. So when these two groups are clearly identified, then you can know the boundary across which the system is oscillating. Major source of damping in the power system, any resistive load that is a inherent damping provider in the system. Any rotating load that also provides some damping, because they also have the same governing equation. So they will also provide some kind of damping. There are some certain extra windings are placed in the generator rotor. So you know that amortizer windings are there. So that also provide some damping. And excitation PSS, excitation control, the supplementary control which is called PSS, that also provide damping. And other than that, POD is similar like PSS, but it is used with FACS and HVDC devices to to modulate their power flow. Now, why power system is poorly damped, or what affects the damping of the power system, that has been already explained piecewise previously, like that fast acting excitation system can provide some negative damping, weak interconnection, heavily loaded tie lines. All these are the root cause of poor oscillation, a poor damping of a oscillation in the system. And also the poorly tuned controllers are also a reason, or we can say this is some tool which can be used to improve your damping. So when they are not properly tuned, they cause poor damping, but if they are properly tuned, they can provide good damping in the system. So as already discussed, what tools you can use to improve the damping? You can strengthen the tie line, or you can put more lines to improve the system strength. You can reduce the tie line loading, or all these things. And then the most importantly, you can tune your power system oscillation damping in the FACS and HVDC device and PSS in your generating unit.
Generator.
Yes. So this is like generator overall schematic diagram. Now generator, we know there are many kind of excitation system. One could be brushless, one could be static. Statics are very fast. They can provide very high initial response, and which in turns cause some small signal stability issue. And that time PSS will comes into picture and will help you to improve the system damping. So these are the modern excitation systems like benefit. I'm skipping all this because I think we are running out of time. And mostly we have explained this, like how PSS works. So this that in the initial slide we have explained this only. As this is constant excitation where it is in the positive direction of synchronizing torque as well as damping torque. But when you add some fast component, the resultant may comes into the negative side of the damping torque. And again, if you provide some kind of supplementary control like PSS, then it will again brings the damping torque into the positive side. Now, why we need fast AVR? Because fast AVR improves the transient stability. So it's improved the transient stability because in the first stage, when during a when a fault happens, what happens? The voltage of the system depressed, and that time using this fast AVR and high response initial response AVR, the generator tries to improve the system voltage. So that is helpful. It is not negative, but sometimes it's can leads you to the negative damping region. So that times again using another supplementary control, you can nullify that effect, and overall the system performance will be very good. So you can see that whenever there is a sudden change in the excitation system, what's happened? Generator electrical power also change. Why? Because we know that flux almost same. Flux remains same. Flux are not changed immediately like the voltage, and we know from the equation that the power output is nothing but V1 V2 by X sine delta. So delta is fixed, everything is fixed. Suddenly V is changing, that's why some power output is changed. But what happens next? Eventually delta changes when you changes in this excitation, and again power output becomes comes back to the original value. It cannot give you like sustained response or increase in generation. Sustained increase in generation is not possible without any mechanical input, but it can cause a change in the momentary change in the electrical output. So what will happen if any oscillation is taking place? If we change the excitation voltage exactly in the opposite direction, what will happen? This oscillation will die down very quickly. and that is exactly being done by PSS. Now, this how it is sensing the oscillation, that depends. Some PSS can just sense the speed. Based on speed, it can operate. That means the generator speed is acts as an input. Sometimes generated electrical power acts as a input to the PSS, and sometimes you know that nowadays this PSS2B, PSS2A, all these are dual input, where these what you can say, speed and power both are used, and using that complex PSS structure, we basically try to rebuild what is the accelerating power, and based on that accelerating power, we modulate the excitation voltage in phase with that accelerating power. So because even we do this modulation of excitation voltage based on the power output, but in the sensing and taking action, there will be some delay. In any closed loop option, you know that this delay may cause what you can say, this instability issue, or some gain is limited by this delay. The action that the amount of action that can be taken is limited by this delay. But if you can predict this accurately using the accelerating torque, then you can accelerating power or accelerating torque, then you can take some advanced action, and based on that, your effectiveness of PSS will improve. Now let us come to some practical examples. So this is one case is shown here. Here, plant in plant C, 2 into 500 megawatts units are there. These are connected to the 400. Then there is 765 kV. Then another in the 765 kV, another generator is connected. From the 765 kV, outside buses are there, and it is connected to a very strong mesh grid. All these. Here you can see that when PSS was kept out of service and certain kind of fault happened, that time very high oscillation, and magnitude is 823 megawatt peak to peak. This is the magnitude of the oscillations. That means from the if you take the second oscillation, then from this point to this point, it is 8. And after the PSS is taken into service, but it is not poorly damped. That time also you can see it is 323 megawatt peak to peak oscillation. But after you tuned it, you can see it is only dying down within 2 to 3 cycle, and peak also has reduced. Now, what are the different? Just one second. I think I can finish it in 5-10 minutes. Then we can take some question.
Yeah, sure. Yeah, it can continue.
Yeah, reason. These are the different kind of reason, and what are the impact that has caused by this kind of oscillation, that is being summarized in this slide. So in the reason, I think already it is mentioned. Whatever we learns in theory, that is the practical reason only. Now, what is its demonstration and what is its commercial impact? What is its technical impact? That you can see from this right side. That it can cause tripping of a transmission line, it can cause a tripping of a generating units, and it reduces, as one of the reason is high loading of your tie line from one region to another region. Then when there are probability of oscillation due to this high loading, then what happens? This transfer capability from one region to other region is limited. So now we know that nowadays the resources are very skewedly spaced in India. Those solar generators are mostly in the desert region of Rajasthan. Now, if we cannot transfer that power to Manipur or West Bengal, then what will happen? The overall cost of operation will very much increased, and that's why curtailment of interregional TTC has a huge commercial impact, and so we cannot do this. Like so if there is any oscillation is there, we need to tune some PSS and immediately rectify it. Otherwise, it has some very high commercial impact, and it will lead to suboptimal operation of our power system. And wear and tear of generator rotors and shafts, these are very common. So, and wide scale blackout, that has also happened in linear grid due to this kind of low frequency oscillations. Here, this is a 0.2 hertz oscillations between the group, new grid and SR grid. So we know that in 2020, before 2013, the SR grid and this new grid means WR, ER, NER, and NR. These four region was synchronously connected and SR was separated. So that time SR and new grid was separated, and in 2013, I think in the December month, it is connected with some 765 kV line in Raichur Solapur. So that means it is very poorly connected. These two systems is connected by only two very weak links, and that's why these two systems used to oscillate against each other. And here the signature of the oscillation that is being captured in the PMU. It is 0.2 hertz oscillations, and you can see these are the different groups. So in the SR side, these are the SR generators, and this side all the new grid generators. They are in sync. There is not much of deviation between them, and it is basically between two areas. So this is inter area. Now again inter area, but it is like previously what was happening, a WIG, the total southern region was oscillating against the total northern. By northern, I am like covering all the region, like WR, ER, NR, all that. So that two are very big power system, and there are a lot of generators in each side. That's why the oscillation frequency was very less. Now here, what happens? A small area in the between eastern and northeast northeastern and western grid that oscillates against each other, and that's why here the frequency is little more. And you can see, as I was telling, that few are the generators that are in the 90-degree plane, not purely against each other. So that means these generators from that eigenvalue also, you know that these generators are not participating in this oscillation. They are indifferent to these oscillations. Again, this is inter and intra-plant oscillations. So here you can see that oscillation frequency is very high, 2.4 hertz. And these are the signature of the oscillation, and you can see that only one or two frequency here. A lot of other PMU plots are there, but only one or two are oscillating much, and other are like there is not much deviation. So you can like as already explained, these are captured only in the local frequencies. This is not reflected in the global. Like here you can see that almost in most of the stations the oscillation can be seen. Here only in the participating plant and few nearby plants this is like visible, and in rest of the system there is no oscillation. This is the controller, like this is the malfunction of the controller, and this is creating a forced oscillation kind of thing. That means if we know that HVDC operates in a certain power level, 1000, 500, like that, we don't continuously change it 10, 20, 35, 100, 500, like that. But now say if your controller is doing this due to some malfunction, then what it will create? It will create some forced oscillation, and in this, generally the oscillation frequency are very high. So here it is a almost 5 hertz oscillation. You know that generally this inter area, intraplant, all these are within range of 4 hertz, but here you can see it is 5 hertz. And even with this lot of renewable coming, this forced oscillation frequency of even very high frequency, 20 hertz, 80 hertz, that has been observed all over the world. In India, we don't have any experience like that so far, but this is the experience with the HVDC controller function. This is one of the example of like subsynchronous resonance. You know that when there is a thermal generator and in the evacuating path, there is some series compensated lines are there, as well as there are some HVDC converter. So this caused this is the perfect recipe for subsynchronous oscillation, and this is one of the event that is being observed in the WR region, APL Mundra. Here you can see this oscillations frequency in SSR. It is in the range of 10 to 40 hertz. So here it is very high range frequency, and it will be difficult to observe this in PMU. It will be observed in PMU, but its frequency may not be clearly indicated in the PMU, because PMU sampling rates are some limited. So it will be more clearly visible in the disturbance recorder, where the sampling rates are higher. Now comes to the different kind of oscillation that is being observed with the IBR resources. Now all these are classical oscillation examples. Now with the solar power plant, wind power plants also, there are different kind of oscillations are observed. This is one of the example. Here you can see the upper graph is the voltage and VAR. So there is oscillation in the voltage and VAR, but as the active power, there is no oscillation. So why this kind of phenomena is happening? That can be explained if you if you build the analytical model of a solar power plant, and it has seen that the transfer function between delta P by delta V, that is like a high pass filter, and that's why these low frequency oscillations that are being damped out in the power, even though they are present in the voltage. So these are the different kind of reason for oscillation related to the IBR resources. So main is the system strength and the delay between the power plant controller and the actual inverters in the field. That is one of the major reason. There are a lot of theoretical papers there, and you can also follow those for more details. And monitoring of oscillation, that is already told that using PMU we can monitor the oscillations. SCADA data, it is very difficult, and PMU in Indian system, it has sampling, not I will call it a sampling frequency, it is reporting frequency is 25 hertz. What we can see at control center, that is 25 hertz sampling rate. So that's why theoretically we cannot visualize any oscillation beyond 12.5 hertz, that is half of the reporting rate. But practically it is anything above 8 hertz, it is difficult to see. These are some real-time display that is being monitored from the control room. So you can see these are the inherent modules that are being given by the PMU vendor. Here these oscillations, and in oscillation, so when we talk about oscillation, what are the important parameters? Its magnitude, its phase angles. These are being observed in the monitor, and also what is the damping coefficient. So you can see that these are the plotting of the different modes in the complex plane, and if any of the mode crosses this and goes to the right hand side plane, that means these are undamped oscillations mode, and operator need to take some action based on its it's already like some protocols are defined, if mode is inter-area, then what to do. Then the operator will try to reduce the load in the inter-area corridor. So that means the tie lines of one region to another region. Now, how can they do it? They will change the HVDC flow. In India, we have lot of HVDC across the region, parallel with the AC line. So, if we increase the decrease the HVDC, with that we can change the loading of AC line, and with this damping can be easily seen that it is again bring back in the left hand side. So this is, I am just giving one example. There are some protocols that has been defined, and based on that operator can take some actions. So these are some different action that can be taken by the operator. I have already explained this. So some of the actions need to be, they cannot be taken in the real time, like PSS tuning you cannot do in real time. You have to do it with the help of OEM, and it needs lot of studies. So that are in offline mode. And in real time, operator, if can identify it is a forced oscillation coming from malfunctioning of the governor from a unit, then it will switch off that unit. If it is coming from malfunction of an HVDC, then it can switch off that HVDC. And if it is seen that it is because of inter-area oscillation, because of high loading in the AC corridor, then operator can modulate HVDC power to relieve the AC corridor power. These are different reference where you can find a lot of detailed analysis and things. You can go through this. Now, I think we have already overshoot by 5-10 minutes. So, if anyone has any question, we can discuss. I may go to the chat.
Thank you, Saibar. I think we can go for the QA session. Few of the questions raised in chat box already, I think Chandan sir replied. I think so. Is there any other questions from the audience? Please unmute and ask.
Yeah, Rahul, can I just pose a question, Rahul?
Yeah, please, ma'am.
Yeah.
Yeah.
Yes, it was a very interesting topic, and actually we went through a real feel of what exactly the low frequency oscillation is, and I think this will be a great inspiration for student community to do more studies in this area. And my doubt is actually whether this adaptive systems like for PSS or power oscillation POD is existing. POD is probably associated with fax controllers, I believe, and PSS of course in the conventional systems. Do we have adaptive controllers really existing anywhere in the system?
No, adaptive controller, ma'am, in the sense the tuning of parameter, automatic tuning of parameter, this kind of features is not available in the PSS. In the POD, what is there, based on the system, there are certain sense of automation is there. Based on the fault level, we know that based on the system strength, the gain parameter needs to be adjusted. So in the STATCOM PODs, these features is there. Like they will automatically measure the system strength. How they will measure the system strength? After every day, 2 times, they will inject some certain amount of MVAR, and will check what is the change in the voltage. So based on that, they can detect the fault level at that time, and based on the fault level of current time, they changes the gain value of their controller. So this is little kind of automation or adaptive that is there in POD, but in PSS so far nothing is there. And still this lead lag block the parameters, they are absolutely static. They are not changed online.
Okay. And one more doubt, like we had a very severe blackout in 2012, where only southern region was probably spared because they were not at that time connected to the national grid. But then what exactly is the cause? What I could learn from the literature is like the power system operators were violating the regulations, and because not considering the frequency deviations, and they were going for overdrawal or under Royal, that was the reason. But is it related to a low frequency oscillation, or are they related together? Can you just briefly comment on this? I know it's a very big topic, but then your crucial comments on this 2012 blackout, which happened in India, affecting a major portion, and how it is related to the low frequency oscillation. Please.
Yes,
It's,
I'll just start, and I'll request Chandan sir to take this question, because
yeah,
he was involved. Actually, I did not even join that time, so it will be better if Chandan sir can take
yeah,
this.
thanks, Abha. Yeah, coming back to these things, let me explain you about the 2012. It's means anywhere across the globe, if some blackouts happen, it cannot be single reason, because this complete system going down cannot be through a single cause. It will be certainly, it will be, means many things are coming together, many kind of weaknesses in the system are coming together, and they will combine and make a, means unilateral pattern, and then you do some perturbation at that time, then certainly system is not going to survive. That's what happened in the US 2003. That's what's happened in the 2012 in India. Similar in the Brazil, you can say. Similarly, right now in this year 2023 in the Pakistan also. So things are like that. So coming back to the question of this 2012 blackout. So the means actual issue, if you look in terms of as an electrical engineer. So the thing is that the system means, one thing is that the protection part of that particular line, which was heavily loaded. So that time, this, means zone 3 issue, that when it is encroaching into the zone 3 region, and due to the, means, the load kind of component that is coming, resistive reach component that is coming, and it encroaching into the zone 3 part. Due to that, the protection is operating. That was, means that kind of things were not in general envisaged, those kind of things. And that what happened, and that related led to the tripping of that particular line. And there were some additional force outages. So one, means just imagine the system that one side you have a northern system connected to the western, and on the, let us say, look at the right side of the plane, you have the eastern system, which is connecting the northern system and with the western system. So you have a plane like, means northern system is connected to western, and western is connected to eastern, and eastern is again connected to the northern system. Okay. So, and in case if you trip any of the things in any of the, means eastern to western or western to eastern, something like that, you will have a simple, a longitudinal system, like the what you observe in the Australian system. Australia's entire system is completely a longitudinal system. That's why they face a lot of issue in terms of the stability, and they have taken a lot of action in that regard. So that's what happened in 2012. The system become longitudinal. And when your system become longitudinal, and you are having a western region which is having a good amount of power, and you have a northern region going through the eastern region, basically, so basically it was like a system generator is at the western part. Western is now not connected to the eastern part, the northern part, which is having a load component, too much of load is there, and you are passing it through the eastern part. So what will happen when you don't have the sufficient capacity or the sufficient terms of, the voltage stability issues are there. So in that regard, what happened is that when this large, huge amount of power was passing through the western part to the eastern part, and then going to the northern part due to the loss of the line between the northern and western, then what happened is that due to that, the voltage stability issues has come into the system, due to which severe power swing has come also into that. Because, means when you change this kind of thing, the angular separation in the entire system will be completely long. You have a very complete generation on the western part, you have a load on the northern part going through a long transmission line of the eastern part. Certainly the angular separation will become a very big issue into the system. So due to that, the voltage stability issues, power swing, all these has come together in the zone. And when the power swing center was lying on the, means north to east part, tie lines, then what happened is that on the first day only northern region got separated. But when on the other day, due to the disturbance, already restoration were going on, That on that day, the problem was that this particular swing, basically the swing center, basically the power swing that we were observing in the system on the second day of the blackout, when the northeast and eastern part got blacked out, that day the basically this swing was lying on the western to eastern part. So that's why the eastern got separated from the western. So this was the overall, you can say, in terms of the, means power system people or these. Apart from that, other things are on the regulator side, policy side, all these are there, but those are already on in the reports. But electrical side, this is what actually happened, basically.
Okay. Okay. Thank you. Thank you, sir.
I think this was the first question, right?
Yeah. Exactly.
Hopefully. So certainly means one thing we must know that as a power system means whenever there is a blackout in any kind of country, it completely modifies the entire structure of the power system in that country. 2003 for the US, 2012 for the Indian power system. After that, you see plethora of changes, plethora of things, means modification in the system, a strengthening in the system, a strengthening in terms of the regulation, a strengthening of the system operator, changes, paradigm shift has happened after that particular blackout. And you can see that how we have come out from that, means that blackout of when we were operating a system as 120 gigawatt load, now we have come to the 220 gigawatt load. So this is what the transition has happened over the period of that time. And soon means later on, we are means in the next decade, we are going to have more than 320, 330 gigawatt of the loads.
So very, very interesting, sir. Very interesting. Okay, sir. Thank you.
Sabal, just for the participants, can you go to the slide number 43? Actually, we did not show them this. I think I thought that this would be interesting to show them, basically. Just you can play the, just let me explain them this simple example, basically. So just prior to that, just put it in the full screen mode. Yeah, just let me explain to them that what this example is all about. This is a practical case of oscillation detection using the synchrophasor data in the real time and how the operator were taking the action in that regard. So what you can see is that there is a power plant which is having a 2 units, 2 into 600 megawatt. You can see on the left side that there is a single line diagram is there. So what you can see is that it is connected through a 2 double circuit line with the grid, basically. And these line were quite long line, 246-kilometer line are there. Okay. And without one thing was that based on the state, it is known that without PSS tuning, stability will not be able to be ensured because the angular separation when one line get trips, it's quite high. So that time what Saval has explained, the impedance, if there is a large impedance, the weak connectivity, certainly the power means the whatever the oscillation that you are going to observe from the generating station, it will be quite huge for that plant. So you can see the plant operating at 1000 megawatt. You can see there was a fault on one of the line. It got tripped due to the fault. This transient has resulted in, you can see that around, you can see it has, the plant was operating at around 1000 megawatt. It was oscillating between the 700 to around 1300 megawatt. So you can see that around 600 megawatt plus minus side, the total magnitude of oscillation is. So that's quite severe, and it continued for around 5 minutes. So that's, means very severe for the entire, means that particular plant. So you can see the plot that on this PMU, means this is the PMU display that in the real time, how the operator is observing these oscillations. So you can see on the one side, there is a plot is there on for the mode chart is there. Okay, right. So it is showing that what Sabal explained in the earlier, that if you have left hand plane and right hand plane. So if you are on the left hand plane, you are very good. But the mode, if it is going to the right hand side, it is becoming unstable. So in that case, what will happen is that this is what happened. Then you can see that when this we are getting a lot of information from the PMU that at what time the damping is going down. You can see the oscillation. You can see those plots. Basically, those plots are representing the red one that earlier which is going up and suddenly it is coming down. That you can see in the picture. Basically, the below one, the plots. Basically, in those curve plots, you can see that the red one is showing the damping. The damping has went out to nearly zero. So because you can see that initially the damping is quite very, very low. So that's what the PMU has. And this green one and the yellow one, basically the mode magnitude and the frequency. So frequency, you can see the mode frequency that we are observing earlier when the oscillation was not there. We were seeing some oscillation in the range of some, but its damping was quite good. You can see that it is on the plus side, the red one. And while the oscillation frequency was also on the lower side. But certainly this plant oscillated, and this resulted resulted in the oscillation of the interplant range kind of thing. So in that, the frequency of the plant range has went up. You can see the plot is going up. So one plot is basically representing the magnitude, I mean the frequency of the oscillation. Another is showing the magnitude of that particular frequency mode. So magnitude is also going up, frequency is also going up because of it is a intraplant kind of oscillation or interplant kind of oscillation, while the damping is going down due to this, the PSS was not properly tuned. So later on, based on this information, we basically earlier it was not known that whether the PSS is properly tuned or not. After this information, we contacted the plants and informed them that the tuning has to be checked, that whether it is properly tuned with respect to the whatever the network configuration is there or not. So after that, the retuning was done at that particular plant, and after that, the similar kind of incident of fault happened. And at that point of time, we didn't see any kind of oscillation. And in between those period of PSS tuning to that, the one SPS was designed that whenever there is a fault in the system and one transmission line goes out, let us reduce the generation. So this is what the problem will be coming when your PSS is not tuned. You are not doing the proper activities for improving the damping in the system. Then what will happen is that, as Seval explained, that you have to take your capability, transfer capability will certainly, you have to reduce that transfer capability. And these are the operator action. These are exactly this, whatever I am showing, with the Sabal is showing, basically, these are the practical experience that are the Green India we have experienced, basically. So these are these are the information that is given to operator, what action you have to take, because in real time also, many at times you will not be knowing, like you Sabal explained about the forced oscillation. One of the challenge for the system operator is to detect from where the force oscillation is coming. If it is a local oscillation kind of thing due to the improper damping, PSS tuning, those you can detect because it will be observed at the local level. But the problems comes and if it is an inter-area oscillation, you already know that, okay, there is a weak interconnection, overloading is there, weak means tie line means some tie lines are stripped due to which the angular separation is becoming hard. So those kind of issues can be there. But force oscillation, if somebody is forcefully injecting some oscillation into the system and it gets synced with the low frequency oscillatory mode in the system, then it will result in a kind of resonating scenario. And that resonating scenario that you already know, LC oscillation, if you that resonate, then the oscillation means, the magnitude of oscillation becomes quite severe. And that's what happened with the force oscillation. Yes. And this force oscillation detection is a very, challenging task for the operator who is injecting the problem. So that's why at that point of time, we collect the information from all the plant is being informed that whether any controller is having issue. This is the practical case, practical experience. We have seen that most of the time, either their governor is malfunctioning, valve is malfunctioning, or these kind of issues we have tracked down basically. So we ask basically these power plant that if there is certainly any issue is there, you need to first stop the things rather than just trying to improve that, trying to take some measures. Now, okay, just either you go for the tripping of the unit or you go for, means if the valve is not functioning properly, reduce the generation to a very low value so that this oscillation cannot be, means the force oscillation injection should not be into the system. And other things you can see that how means operator is relying of some information reliance is there. Some on the HVDC side, utilizing the HVDC for controlling the tie line or the AC tie line, parallel AC tie line flows into the from one part of the system to the other part of the system. So those are the measures, ways in which the real-time operator takes the action for controlling these oscillations. So this is just a brief summary on the thing, because it's a very, means a very vast topic to cover, means in such a short span of time. Saval has done a good job.
Yes, sir.
Hopefully,
Yes.
You all agree that Saval has done a wonderful job to come from the journey from the generator point of view to the coming from one single generator to the system-wide problem and how this can be measured and how it can be mitigated.
Yeah.
Exactly.
Yeah. Is there any other question from the audience? You can unmute and ask because
there are some, some chat. One question was there. So
what is the component critically affected by the large power swings during the LFO event? And how can the associated damage be quantified in terms of lifetime production or operational cost? It's a vast question, I think. Yeah.
Okay, what is the large power swing during a LFO event? It is going to impact you also, means at your home also. Means when the large power swing is there, there means when you define the power swings and when you define the oscillation, there are, means in generally we define the power swing during the disturbances, but the oscillation can come at any point of time, because it's a small signal stability issue.
Yeah.
And coming back to the things that, means how this large power swing. So in general, large power swings, means when we talk about the system, if there is a large power swing, if it is a stable swing, it's okay. Otherwise, the generator is going to get out of a step. Okay, because of the it is not able to push that much of power into the system. That's on the side of the transient stability issue. On the smallest signal stability aspect, if there is a large power swing, that means it is an inter-area kind of scenario. Inter-area oscillation means the entire system is divided into two parts, and that's one of the major challenge. When your entire system is divided into two parts and oscillating coherently with each other, means not coherently, in phase opposition with each other, what is happening is a large mass of the generator is oscillating in one direction, and entirely in another mass of generator of the entire system is generating in, means oscillating in other direction. So you see amount of swing that you will, the amount of the Sabal was talking about the mode energy basically. So the energy that will be clubbed, if you club each of the generator, they will be oscillating in positive direction. That means around there, whatever the magnitude means at what point they are were generating, let us say it is 500 megawatt. So each 500 unit, let us say clubbed up together, they were oscillating of 300 megawatt. What you will be going to observe that the tie line which is connecting these two system, basically two coherent, means a different group of generator which are oscillating, those particular tie line will be observing a severe kind of oscillation, because the exchange of power, or whatever the exchange of transient exchange of power that is happening, or the energy exchange that is happening between the generators, because there is nothing which is being generated. It is basically exchange of the energy, that is one is oscillating on upper side, one is going on the downside. So the oscillation exchange will be happening through these tie lines connecting these two group of generators which are oscillating. And when these large groups are there, certainly the tie lines will be observing a severe swing. And in those swing, if this swings, this can result in, means there can be a voltage issue at that particular node. There can be a protection operation, distance protection can operate. The voltage goes very down, or there can be a very high kind of current is there, means high power is going through those tie lines. So power swing and stability, all these things can happen to that. So this is the, means the component it critically affects. Generator is going to certainly get affected due to that. Wear and tear, you will not, problem is that quantifying that will be a big issue, because you don't know the problem until local oscillation problem you will know. But global oscillation, it is happening, they are participating, components are shared by other generators also, then means wear and tear, how much wear and tear is happening, it will be only known in the long run only. It cannot be known in generally in the short term point. Short term point, it will be known only for the local oscillation. When the local, like, means you have seen the problem of the subsynchronous resonance, where you can see that there is a damage to the shaft of the rotor is there. So those kind of things you can observe. If there is oscillation to the generator, you can see that if there is a big vibration is coming into the system, local oscillation are persisting for a longer duration of time, it can result into the, means problem with the capacity, how much power I can evacuate. So direct means you can appropriate, means attribute to the problem there itself. But wear and tear part, means quantifying that will be quite difficult in those scenarios.
Yeah. So one more.
Operational cost somebody has written. I will tell you this operational cost, how you can define is that, let us say power plant can evacuate 500 megawatt. It has created a line, but due to the low frequency oscillation, you have restricted it to 400 megawatt. Certainly the 100 megawatt can be quantified at its operational cost now. So how means that particular plant is not able to export that much of power. If you create a tie line, or if you create a transmission line to evacuate this much of power, or you transfer this much of power from this area to that area, and it get restricted to the low frequency of oscillation, then that much capacity cannot be utilized. So that much of transaction cannot happen from one part of the system to other part of the system. That is also the loss of the reliability, loss of the support that you could extra get from the other system. So those kind of things are there.
Yeah, I think Fran get it's replied. It's very informative. So yeah, so one more final question. It's about the analysis point of view. Actually, we doing this mode based analysis in analyzing the oscillations through Prony or metrics pencil for the measurement based analysis for the past, I think, 10 years, a decade itself. So what we actually where we actually lagging because this analysis point of view. Actually, I am seeing this I mean, the analysis what we followed in is also linear thing. So, is there any modification is Posoko is trying or is lagging for how much it is actually for the analysis point of view?
Okay, so the thing is that if you ask me as an operator that
Yeah,
whatever
I mean,
can give some
I mean
output,
actually,
whatever, yeah,
uh,
just
I'm
please continue.
yeah, I mean actually, whatever Sebal presented in that measurement analysis point of view, even we go for HTLS systems itself, it's actually came 10 years back. Uh, that methods and all. So
Okay,
yeah,
I will
that
just ask you one thing. Why do
yeah.
you think Prony is not good? Matrix pencil
Mm,
is not good. Those are
mm,
not good. Means why this concept is coming out into the system? When
mm,
if you try to see the system from the perspective of means if you have a very good measurement quality that is available to you, and
mm,
based on those measurement, if you have a very good observability of the measurement, and when you go for this kind of if you remove the noises and then you
yeah,
compute these are very good. They are going to
yeah.
provide you a
My
very good
point is
accurate
that
result.
yeah, yes.
Yeah,
My point is that
they are going to provide you a very good accurate result. The issue with that is that you don't have a mathematical model, so you get observability, but no controllability will be there. Controllability, the operator is going to decide based on the information that he gets from the site or he gets from his practical experience that okay, this mode is there. Let us say 1.2, 1.5, 1.6. That is in the intra plant range. He knows
mm,
that there is a problem with the plant, so he will start detecting where this particular issue, where this mode energy is very high. So at that particular point, he is going to ask that whether there is something happening in your system or not. He will start checking the MVAR, megawatt and MVAR value from the SCADA and the PMU data itself, which particular unit of the plant is generating, means having a very significant oscillation in the MVAR values basically, or the megawatt values. So based on those information, he will
mm,
immediately contact the plant, or the nearby 4 to 5 plants can be there. So he will not be able to, he will contacting all the 5 plants and telling them that if there is anything
mm.
happening, stop it.
Yeah,
Basically.
controllability is one of the issue. As I also impressed with that thing. But yeah, what I felt
Prony,
is actually yeah.
yeah,
When
you already know that about the Prony. Initial
yeah.
noise, if you remove, it's a very good thing.
Yeah,
Only it is
yeah.
very prone to noise. If you are having a noisy system or noise, if you put some garbage, you will get garbage. So that's a known issue to the Prony. Prony,
Yeah.
if you remove that garbage part, initial, the transient part, you are going
Mm,
to get the accurate result. Whatever you are going to get from other method, you are going to get from the Prony also.
mm.
That's
Okay.
what our experience is basically. We have, we have utilized Prony, multi-Prony, multi-pencil,
Yeah,
different
matrix
ARA,
pencil also you
STLS,
are understanding,
everything
but
we have
matrix pencil
utilized.
has some limitation with the pencil parameters and all.
Right.
Yeah. That's why I'm asking why we are still continuing that techniques itself. That's why
So that
yeah,
what provides a good result to the operator,
yeah.
we will keep on continue to use it basically.
Mm-hmm.
If you can provide me a very good result
Mm,
from any other system and provide me a result that you can verify that from the different methods, then
mm,
certainly somebody we can certainly go for it. The pro thing
mm,
with the
mm.
pony is that, or whatever because it's one of the simplest curve fitting method is
Yes,
there, right?
yes, yes. Because there is no
And the more
computational
simpler,
effort also less.
yeah, less, the more simpler are the things, the more fast information we are going to get in the real time.
Mm-hmm.
The more complex algorithm, because no, the number of PMUs that is coming into the system, it is more than 1400, 1500 kind of things.
Yeah.
And we compute about the Indian power system, more than 1600, 1700 buses, you can something like that. If you have PMU at each of the buses, and you only just take one parameter of voltage, one parameter of frequency, one parameter of angle itself,
Mm,
you can see the computational effort that will be required if you have a very complex kind of algorithm in place. So those
mm-hmm.
kind of thing will certainly not going to provide you much. You don't want to get a very, means too much of, means accuracy, means or the precision or something like that. You want to
Mm.
get a result which is practical, which can be utilized and which can help the system, which can safeguard the system. That's
Yeah.
what the intention is
Mhm.
there. So
Yeah, yeah,
that's why if you see many of the operators are still, means the pronies are still, it's still the, means continuing with, it is what, it will be one of the method that will always be available whenever there
Mhm.
is algorithm is there. Yeah.
Yeah, yeah, yeah. Okay, okay, okay. Fine, fine. Okay. Oh, is there any other questions from audience? Shall we wind up for that? Any
Hi,
questions and all?
hi, Rahul. Is it possible to take
Yeah.
up this last question? I was just waiting for just to take this. Yeah. Mr. Chandan and Mr. Saibal, thank you so much for the presentation. And I have a question on the algorithms which they use, say the optimization algorithms which they use for the power system stabilizers. This question is exactly opposite to the analysis. It is like one, you have presented the online method of analysis. What I am asking in the question is an offline method of analysis and how far it is being applied into the systems, because there are many optimization algorithms coming into the picture, which is showing dominant results. And is it being implemented practically in our power grids? That is my first question. And second question is regarding the virtual inertia. And is there any practical implementation into the conventional grids to maintain the stability of the power system? Over to you, Mr. Chandran.
Yeah, several
Yes.
virtual inertia, you can answer better than me. Yeah. So I will, means first you
Yes,
can answer the.
actually, in
Yeah.
Indian system, still now virtual inertia is not being implemented because in Indian system, inertia is still not a problem. We have enough inertia. Still, most of the our generator fleets are conventional generator only. But in Australia, if you want to learn about this virtual inertia in Australia, there is one big battery has been installed by Tesla, HPR. This is the name of the plant. I did not remember the complete name. So you can search and you'll get it. So there they have implemented the inertia, virtual inertia from the battery, and it can give response. That is an experimental setup only. But so far in any other country also, like this virtual inertia, it's not that much has come. Only in Australia this is there, and in other country this is called like fast frequency response. Like we know that governor response comes into picture after 5 to 10 seconds like that, but if we can activate the response even before that, like for the IBR resources or from battery, if we can activate the response before that, that is being termed as fast frequency response. But which is purely inertial response, that is virtual inertia, that is only there in the Australian system. So you can read all those documents for that. And for optimization, I would like to just take this question. Optimization in the sense, there is one IEEE guideline for power system stabilization, via excitation control. One this tutorial is there. There you can see clear-cut guideline is there, like how in practical system these like optimization means your these parameters of this lead lag compensator and the gain value of the PSS. This needs to be optimized. So for that, there is some clear-cut guideline like how you can do this so that it ensure enough phase lead in the like your frequency range of interest, which is 0.1 hertz to 4 hertz. So in the entire frequency range, the phase lead should be in the range of 30 to 40 degree, to ensure that there are certain method like gain you increase, keep on increase, and at what time there is some oscillation even without any disturbance in the system, that time you stop. Like that, for this is used for gain, for tuning of this lead lag time constant. Also there are some guidelines. Most of the vendor use that only. Now some there are a lot of papers where like many optimization algorithm that are being discussed, but in commercial application, you know, the reliability and robustness of the algorithm is of highest importance, and that's why like not many optimization technique that are discussed in technical paper that converts into an industry application.
Yes, thank you. Thank you so much for this detailed explanation, Mr. Saibal. And the way you have narrated the whole presentation was also good, since as a person who's working in power system stability analysis and the dynamics, I could relate to it very well. Thank you. Thank you so much.
Thank you. Thank you.
Thank you, Grace. Shava ma'am, may I
Grace,
invite
if
for
you
your vote
can,
of
I
thanks?
have shared one paper basically that the Indian power system experience that that's game means in that paper, if you go through that, you will certainly not be finding many paper on the practical aspect of the power system tuning. So that's one of the unique paper that I have shared in the link also, that how the PSS tuning experience, corroborating the theory, practical aspect, limitations, challenges that you observed, vendors, how the different vendors perform these kind of things. So there is a very big comparison and all those details are available. Hope I think that may also help you in getting further insight into the issues that you have asked on the optimization.
Yes, definitely, definitely, Mr. Sandeep Kumar. I'll just go through the paper, and maybe in future we can sit for the discussions on the same.
Sure, sure. Thank you.
Yeah.
Thank you, Grace. May I invite Shava ma'am to get the vote of thanks?
Yeah, thank you once again, Rahul. And it was really a very fantastic session. And I would take up this opportunity to express our heartfelt gratitude and extreme level of happiness to Mr. Saibal Ghosh and Mr. Chandran Kumar from ERLDC Grid Control of India. It was a very fantastic session, and in fact, you have answered the questions, and in fact, this being a very technical topic, and but the time you have utilized very well, and it could give a good insight into people who have been working with power system. So many thanks for joining us and making this program and sharing so much of knowledge from the practical side, which is often very difficult for we academicians, because it was really useful for us. And I take up this opportunity to thank Rahul Satish for arranging such a excellent session. And also, of course, we have a lot of participants who have joined from various parts of the country as well as abroad as well. I think different time zones as well. So there was a very good interaction, and interaction time, of course, it was more than nearly 1/4 of the session itself. And once again, thanking each one of you, I conclude. Thanks, and have a nice day, and good night to all of you. Thank you, Rahul.
Sir, may I share your mail IDs too in the chat box?
Sure, sure, no problem in that.
Yeah, I am sharing.
We are better approachable through the LinkedIn's.
And Rahul, if
Yeah.
we can have the
Yeah.
copy of the presentations, it will be very helpful. So like,
Yeah, it will be
we
streaming in YouTube itself. No issues with that.
no
Thank you.
issue. And that link also you have copied, no, Rahul? But whatever has been shared by Chandan Kumar.
Yeah, I already copied. Yeah.
Okay, you can share it with
That
me.
I will share to you. Yeah, sure.
Thank you.
Thank you, ma'am. Thank you, Blossom. Thank you, Saibal.
Yeah. Thank you, Blossom,
Thank you,
for
sir.
being
Thank
with
you,
us,
thank you.
and very good participation. Thank you. Good night.
And
you, sir.
yeah, audience, please write your genuine feedbacks to us. Then we can improve our programs too. I will write our speakers mail ID here itself. Thank you, Blossom. Thank you, Chandan sir. Bye bye.